Hello.
So next is Marina Nikolova from, I'm not sure, where are you from?
I'm from EMBL Hamburg. In fact, there's an EMBL site here at the SRF campus. I'm, however, from Hamburg, not from here. So this is going to be about what we do with our X-ray imaging at our P14 beamline in Hamburg. To give some context, P14 was designed and constructed as a crystallography beamline. So our imaging setup, X-ray imaging setup, there is relatively recent from the last few years. And now it has developed so much that, in fact, about a bit more than 20% of the beam time at P14 is dedicated to X-ray imaging. The setup consists primarily of a PCO camera that is situated on a big detector stage next to our crystallography detector, the Eiger. And when we want to switch between the two setups, we simply move this big detector stage laterally. The PCO camera sits also on a small detector stage that we use during collections to move along the beam backwards and forwards by a few millimeters. This is already our second iteration of a PCO camera. It is the same as our first one, a 4 megapixel size running at 100 hertz at its max frame rate in full ROI. The only difference between this camera and our previous one is the new driver that we got, that we're running now on Ubuntu 22. It turned out that it's more stable compared to our previous version. So the data is extracted from the camera by our PCO camera server. It is sent over to Arapaho over 0MQ and 40 gigabit connection. Both are in-house developments. Arapaho is finding the best matches between each projection and each of the 100 flat field frames that we are collecting. And is doing flat field corrections live during the collection and sending those for live display. Then dumping the data to our BGFS storage, which is here in the rack. This is also our second iteration of BGFS. The previous one worked very well, but got old. And now this one is about 1.7 petabytes big. Once the data hits the disk, it is immediately processed using our cluster, consisting of 13 nodes here, each 88 cores. Both of the BGFS and the cluster are shared between all of our beamlines and end stations. The type of samples that we put at the beamline are tissues, plants, insects, plankton. Here we see an example of mouse kidney and a plant root nodule, both courtesy of Jonas Albers, our X-ray imaging specialist. This is what our data acquisition and reconstruction timeline looks like now. We collect 4 distances in less than 2.5 minutes. We immediately trigger the processing, which consists of flat field correction, phase retrieval, and 3D reconstruction. And this processing part finishes for the simplest case of 180 degrees collections in 30 seconds or less. What TomoCTF, our processing software, does is, first it's triggered automatically by MXCube. MXCube is our GUI, which the users see and use for starting the collections. we heard the talk that we almost missed by Antonia just before lunch, that MX-Cube is for crystallography. In fact, we reuse it also for X-ray imaging. It knows beamline parameters like energy, like the prefixes of the files, and all of those are written immediately after the collection in a parameters file that is then used as input for TOMOS-ETF. Additional command line arguments include input, output directories, log directory, how many cores we are running. Then we proceed with the flat field correction. The first step is doing cropping on the images. Then we divide by the average of the 3 best matches from the flat field frames. This is the header of a sample header of a TIFF file consisting of the matches that Arapaho found live during the collection, and the indices here of the 3 best matches that TOMOS-ETF simply takes and uses directly. The phase retrieval starts with the shifts, finding the shifts between the 4 distances. We are suppressing some frequencies in Fourier space. Then we do padding based on what's in the config file or in the parameters file, and then we use the contrast transfer function algorithm on 4 distances as discovered here at TSRF, in fact. Then we do the rotation center based on 10 frames. We take the average of 5 rotation centers. We store the result as a sinogram, not to disk, but in memory. And we proceed with TOMOPy's grid rec, used as a library. However, we don't use any of the Python routines. We use GridRec's C routines directly. When we run on one cluster node, the node does all 1,800 frames, and the node gets all line number 1 from all lines number 1 from all frames, and that creates a sinogram, a total of 2,040 of them. The picture when we run on 2 nodes looks like this. Each node does 900 frames and respectively gets 900 lines of a partial sinogram. Each node gets at that moment 1,020 frames and receives the remaining partial sinograms from the second node. And it's exactly the same when we go to more than 2 nodes. So we do a lot of parallelization using POSIX threads and MPI, and we are heavily multi-threaded, and for us that works very well. For splitting between the nodes, we use MPI that we start via SLARM. We have 1 MPI process per cluster node, and we use remote memory access by exposed windows in MPI. So in terms of live performance, for a single 180-degree collection consisting of 4 distances, each frame being 4 megapixels, and a total raw input data size of 60 gigabyte, and an output size of also 60 gigabyte approximately. It is that much because we in fact write the intermediate CTF frames to disk. This is not needed, but is just nice for debugging. And with those parameters, we get to 65 seconds per node. And at the beamline, we in fact run with 4 nodes always. And that results in about 30 seconds per node. During the SRI, Dectris announced their Dectris Cloud, and were very kind to give us a node to test. And on one of the Lightspeed nodes running, consisting of 192 AMD cores, we get 30 seconds processing time with reads and writes from RAM. This is, however, a simple case, and I have here a single 180 highlighted because at the beamline, we have a slightly more complicated case when we, in fact, do queued collections. So MXCube allows for queuing of collections, and that puts a little bit more pressure on the system, especially when at the neighboring beamline we run crystallography experiments with the 16M Eiger. So this is the log, an excerpt from the MXCube log from about 10 days ago. We see a lot of, so this is just the timing of how much the processing took. We see a lot of times below 30, but we also see some above 30. In fact, the medium of this happens to be exactly 30 seconds. Those two runs here are a bit slow because at exactly that moment the Eiger collections were running at P13. Now, thank you. The previous was a single 180-degree collection, but what I just showed. But we also now do what we call extended field of view. I think in the diamond talk they called it double field of view. For us, it's not exactly double because we need about 450 pixels to overlap the left and right frame that we put together. So compared to what we do in the processing to what I showed just before, now we process 2 projections at a time, and the additional operations that we have to do include finding the shift between the frames in each 180-degree pair, flip 1 frame, glue the 2 frames, and here we have an example of frame glued, so 2 frames glued together to form 1. Then we apply a mask to remove some cutouts. This has been the work of Angelika Svetlova, who developed this in Python originally for her EMBL track samples. How long does this take? Well, we have double the input size, 4 times the output size for a standard collection. And on the 4 nodes that we normally use, this takes around 70 seconds. Now, this is a reconstructed slice of those track samples. They contain plankton, but also a lot of salt. Salt is extremely difficult to reconstruct. And if there's a shift of 1 pixel or less even, one is able to see that. So one has to be quite precise. Now, we don't have live reconstruction yet, but we have those live viewers, ADXV and an FFC viewer, where ADXV reads raw TIFF files from BGFS. The FFC viewer displays flat field curated JPEGs received over our TINA control system. Both are running or displaying frames at the rate of 25 frames per second and 23 frames per second respectively, where the TIFF files are about 8 megabytes big and the JPEGs are just below 2.5. Now the next question is, can we get live reconstruction? That would be the next step. In summary, and the outlook looks like this. We have at the moment 30 seconds reconstructions for single 180-degree collections. Our extended field of view collections are on the order of 70 seconds processing time. Challenging points are when we have queued 180-degree collections, when we execute many of them in sequence. Yet more challenging is when we have 360-degree collections that are queued. And I didn't dwell on that, but we have queued collection in order to do stitching on those images subsequently. Currently, we do the stitching offline, and it's relatively slow, on the order of more than half an hour. The question is, can we get this to be automated, executed at the beamline, and fast? At the moment, we don't have compression in the software. Our only compression is on the BGFS level, so BGFS compresses the TIFF files for us. But can we get even more compression? And the next question for the future is 1,800 frames enough for grid rec, or is our scan a bit undersampled? And with that, I would like to acknowledge all the people who have been involved in this work. Gleb Borenkov is the mastermind behind the whole setup. And we have been working very closely with Liz Duke and her imaging team. And this wouldn't have been possible at all without our Hamburg IT support. Thank you.
So, unfortunately, we went a little, just tiny bit over. So I'm going to ask that you also email. No, there's some. Sorry, unfortunately, you're gonna have to get her a coffee.
I'm glad to run away.
You're glad to run away.